Okay, today is Module 4, Lesson 22. We're still working on writing and evaluating expressions, but today we're going to focus on exponents. So let's review exponents. We've done them before. So if we wrote a plus a, how would we write that? What term would that be? A times 2 or 2a. So it'd be like 1 plus 1 is 2, 2 times a. Two groups of a, right? But if we had a times a, how would we write that?
2 squared.
A squared, or a to the second power. That's how it could be written, okay? So remember that the first one is multiplication is repeated addition, and exponents are repeated multiplication. And that's what we're going to look at today, the repeated multiplication. All right, so we're going to try a little experiment. Everybody took from the outbox a sheet of paper, either pink or blue. So what I want you to do first, don't fold it, don't do anything. Write in your notes a prediction of how many folds you think you can make. Don't fold it yet. How many folds do you think you can make? Write your prediction on your paper. Okay? So now, before we fold the paper, how many folds do we have right now? We have 0 folds. All right, if you're at home watching the blog, take a sheet of computer paper or a piece of loose leaf paper and you can try this. So we have our sheet of paper, 0 folds gives us how many layers of paper? 1. So if you look at the table in your notes, 0 folds gives us 1 layer of paper. To write that in exponential form, which means with an exponent, in exponential form, it's 2 to the 0 power. So what can we say about anything to the 0 power? The answer is 1. So you might want to write that in your note that anything to the 0 power is 1. Anything, any number, any variable. Anything with 0 as their exponent is 1. So right now, 0 folds give you 1 layer. So now you're going to fold it in half, as close to half as possible, any direction you want, hamburger or hot dog. Crease it. So now my 1 fold, how many folds are there? 1 fold, but it gives me how many layers? 2 layers. So my 1 fold gave me 2 layers. So how could I write that as an exponent? 2 to the first power. The number of paper layers written as a power of 2. All right, so does everybody see 2 layers? So now if I fold this in half again, my 2 layers, I'm taking 2 layers, putting them on top of each other. So fold it again. Now how many layers do I have? 1, 2, 3, 4. So 2 folds gave me 4 layers.
Is anything to the first power itself?
Yes. Does everybody see the 4 layers there? 1, 2, 3, 4. Open it up a second. How many sections are there? 4. Okay, fold it again. Keep going and filling in your chart. Count the layers. So we went from 4 layers. We're going to fold it in half again. So these 4 are now going to fold on top of my other 4. So now how many layers are there? 8. So 3 folds gave me 8 layers. See how many times you could fold. I'm going to pause the recording and let you keep working. Okay, it's pretty much impossible to get more than 8 folds. So let's look at how we filled in our chart. All right, so on our table, 4 folds gave you how many? 4 folds would be 16, so that's 2 to the 4th power. 5 folds, 32 layers. 6 folds, 64 layers. 7 folds, 128 layers. 8 folds, 256 layers. Well, somebody said they folded at any time. Did you really count 256 layers? That would be pretty difficult to count all those teeny tiny little layers. Okay? So were we able to continue folding indefinitely? No. How come? Why did we have to eventually stop? What happened to the stack? The side that we kept folding kept getting too thick. So the stack got too thick on one corner. Because they kept doubling. Hopefully you're taking notes, not playing with the paper anymore. So could we use a calculator to find the next one? Because we can't fold the paper anymore. It's physically not possible. But if we wanted to fold it again, we could still find the answer with a calculator by doing what? Yeah, multiplying it by what? 2, excellent, right. Notice we didn't keep adding by 2. We kept multiplying by 2 because 2 was the number of layers. That's where the 2 is coming from, how many layers there were, okay? So when it kept doubling, 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 doubling. Multiplying it by 2. So now what is the relationship between the number of folds and the number of layers? We want to make sure we include all those pieces of information in our answer. So include as the number of folds. This is like science when you're writing your statement, how you have to include the relationship. As the number of folds increased by 1. Can we shut the door, please? Thank you. So what happened to the number of layers? As the number of folds increased by 1, I folded it once. What happened to my layers? What happened to the layers, Naomi? They doubled. So when you're writing about a relationship, you have to say, as one does this, the other does that. And you should have heard that in science too. As one does this, the other does that. So it's looking for the relationship. So as the number of folds increased by 1, the number of layers doubled. How is this relationship represented in the exponential form? So in the exponent, what are the two, first of all, what are the two parts of exponential form? What are the two names of the two parts? Perfect, the base and the exponent. So what was our base and what was our exponent? Look at the table in your notes. What did we use as the base? What did we use as our exponent? We use 2 as the base. And we use the number of folds as the exponent. now, if the exponent is the number of folds, and we don't know how many folds there are, if we wanted to keep going, we could use f as the number of folds. So what expression would we use? What would our exponential form expression be? 2 folds, number of layers, we don't know what it is. What would it be?
2 to the f power.
Perfect, good job. 2 to the f power. Now, instead of folding it, it would have been easier if we cut it. Because if we cut it, it wouldn't have gotten so thick on that end, and we could have kept going. It was the folding that slowed us down. So if we cut it, we could have kept going, and we would have gotten the same answers, okay? So now, if we wanted to write an expression that describes how many layers of paper resulted from 16 cuts, so like 16 folds, how would we write that in exponential form? They want an expression.
2 to the f power equals 16.
Well, f is now 16. So 2 to the 16th power. They want you to evaluate that now. Who wants to sit here and do 2 times 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 2? 2? I don't know, I just lost count. Could we do it? Absolutely. Could there be an easier way? Absolutely. So here's what we're going to do. We're actually going to take a timeout from lesson 22, and I'm going to interrupt it with a quick calculator lesson. Because your state tests are next week, final exams are in a couple of weeks, and you are allowed to use the calculator for some parts of it. So I just want to go over how to use the calculator. So right now, everybody take a calculator. And first thing I want you to turn it on. There's the on button on the bottom left. Oh, take one from one of the other tables. I'm short too. Alright, so the clear button is up here on the right if you need to clear it. So just do, 3 minus 2, 4 times 5. Make sure you hit enter. Notice when you enter the equation, it shows you the whole equation in the screen still. So you can see exactly what you entered so you know if you entered it correctly or not. Alright? So now how are we going to use this to help us with exponents? Everybody clear your screen. There's 2 different ways we could use the calculators for exponents. The first one is just using the squared button. Okay, so if it's to the second power, we've got a number right away. So if we wanted to do 4 squared, everybody hit clear. Hit 4. Then hit the button that has the X with the squared on it. But hit enter after. You have to make sure you hit enter or the equal sign. And what does your screen show you? Should say 16. Exactly. Alright? Now, suppose it's not squared. Suppose it was 4 to the 5th power. If I had to do 4 times 4 times 4 times 4 times 4, I might lose track. Did I hit it enough times? So on. So what we could do is use the button right above it that looks kind of like it's called a caret, a chevron, whatever you want to call it. So here's what you're going to do. Clear your calculator. 4. Hit that chevron or arrow button. Hit 5. And then hit enter. Did you get 1024?
No.
Okay, so that's how you would use an exponent other than 2. Okay? Now, we did talk like once about this thing called square roots. What's the square root of 25? 5. How do we do that on the calculator? So if you look at the x squared button again, look right above it. Do you see how there are light blue things written in on the screen, on the calculator, but it's not on the button? What you have to do is hit that second key on the top left. Once you hit that second key, that activates, it changes the button to do what that light blue thing says. So instead of doing the squared, we want to do squared root. So right now, everybody clear your calculator. Hit the second key. Hit the x squared key. Hit 25. Then enter. Did you get 5? So that second key enables all the light blue functions that are on the face of the calculator. But we should need to know that. It should just be addition, subtraction, multiplication, and division. Then now you see how you can do exponents on your calculator. Okay? So now let's go back to our lesson, 2 to the 16th power. So figure that out on your calculator. So clear it, 2, the chevron button, 16, enter, what'd you get? 65,536. Much easier to hit 3 buttons on the calculator than to multiply that out each time, because we're more likely to make a mistake. All right. Yes. Scientific, not graphical, correctly. Scientific calculator. So let's take a look at these lovely bacteria. Ugh. Bacteria can just multiply and multiply. Bacteria are microscopic, one-celled organisms that reproduce in a couple of different ways, one of which is called binary fission. In binary fission, a bacterium increases its size until it's large enough to split into 2 parts that are identical. Hold on! Why can't we get chocolate chip cookies to do this? I don't understand. Scientists are totally wasting their energies in the wrong things. All right. So anyway, these 2 grow until they're both large enough to split into 2 individual bacteria. So this one becomes 2, that one becomes 2 more, that one becomes 2 more. Big pizza, chocolate chip cookies, no, really, we can't figure out how to marry this with that? But anyway, so this keeps growing exponentially, as long as growing conditions are favorable. So let's take a look at this chart and record the number of bacteria that result from each generation. So our first split, 1 generation gave me 2 bacteria. So that's 2 to the first power. So then 2 generations, here's 1, here's 2, gave me how many? 8. So that's 2 to the third power. So take a minute now, and with your calculators, fill in the chart. All right, let's take a look at the answers. Okay? So every time it was multiplying by 2. I'm sorry, it was doubling, right? Multiplying by 2. Are there any questions on this chart? All right, we're actually going to skip the next couple of questions because, quite frankly, I think some of them are silly. And let's take a look at D. Write an expression for how many bacteria would be present after G generations. So how would we write an expression? We don't have to evaluate it. We don't have to solve it because we don't know how many generations there are. So let's put the calculators down, please, and think about how we would write this expression. Right, exactly. 2 to the G power. Now these would also come in handy for our friend volume. All right, let's take a look at the last example. This box has a width W. The height of the box H is twice the width. So the height is 2W because it's twice the width. The length of the box L is 3 times the width, so it's 3W. So the height, the width, and the length have a ratio of 1 to 2 to 3. Stay with me, please. For rectangular solids like this, the volume is calculated by multiplying the length times width times height. You know that already. So we always start by writing our formula. Then we replace the letters with the numbers. So the length was 3W. The width was the width. The height was 2W. We know that 3W is 3 times W, and 2W is 2 times W, so now they expanded it and wrote it all out. We know that 3 times 2 is 6, and what's W times W times W? W cubed. But we would still have to label it like feet cubed or inches cubed, whatever it might be. Okay? So let's take a look and let's follow the example to calculate the volume of these rectangular solids given the width W. So if it was W times 2W times 3W, W equals 1. So 1 times 2 times 3 would be 6 centimeters cubed. But now suppose the W was 2. So we have 2 times 2W times 3W. Do you see how I replaced the W with a 2? So then that would be 2 times 4 times 6. It should really be written top to bottom on scrap paper or note paper. 2 times 4 is 8 times 6 is 48. So this would be 48 centimeters cubed. If the width was 3, 3 times 2 times 3 times 3 times 3. So 3 times 6 times 9. Woo, we're getting some more big numbers in here. Since the bell's going to ring, I want to jump down to the last one, make sure we get the last one done. So we have W times 2W times 3W. So what do I get when I multiply that together? Kind of looked at it on the first page already. What's 3 times 2? 6. What's W times W times W?
W cubed.
Right, but we also have to label it centimeters cubed. It should be cubed. I don't know what I wrote, or if it got blocked in there, or I messed it up, but it should be cubed. So good question. Okay. So in closing, we have to remember that 5 cubed is different than 5 times 3. 5 times 3 is repeated multiplication. 5 times 5 times 5. 5 is the factor that will be multiplied by itself 3 times. 5 times 3 is repeated addition. That's 5 groups of 3. 5 plus 5 plus 5, which is 15. There's a big difference between 125 and 15. Please put the calculators away neatly